Welcome back, guys, to another Mr. Hutton Science online lesson. This time we're on the topic of energy changes. So this is the AQA course and it's topic 5, so it's in paper 1. And the first lesson we're looking at today is exothermic and endothermic reactions. For those of you on the AQA course, here's what the specification tells you that you should know. So pause the video now if you want to read through that. Right, so at school we would have a quick discussion now about what's happening when we burn things and also what we use that fire for. Okay, so what I want you to do, if you're at home now, if you're learning online, then just pause the video and discuss that with your family. Otherwise in school we'd discuss that as a group. So, what is happening when we burn something? Well, we're really burning. Combustion is when we react a fuel with oxygen. Okay, so it could be a gas that we're burning, or it could be a solid like coal or wood. Okay, but we're reacting them with oxygen. So there's a reaction going on. All right, and with burning, we actually get a lot of heat coming off, so it's quite often used to heat homes. Lots of you will have fireplaces at home. It's used to heat water, to evaporate it into steam, and that then drives turbines that then create electrical power for vast areas. So we use that energy that's coming off from that reaction, and we put that to good use. Right, again, if you're at home, just pause the video now and have a discussion or think about these by yourself, or maybe do a quick bit of research on the internet. Okay, at school we'll discuss these for a moment. So what is photosynthesis? Photosynthesis is a reaction. Okay, it occurs in the green part of plants, and it's where carbon dioxide and water are converted to oxygen and glucose. Alright, so this is another chemical reaction. Now, it only occurs during the day. And quite often when you write this equation out in your biology lessons, you'll put a word above the arrow in the reaction. Okay, and that word is usually light. Now then, light is a form of energy. Okay, so this reaction actually requires energy. It takes energy in. Okay, so the difference to combustion there. Combustion gives energy out, but photosynthesis, that takes energy in. Right, so what do these examples tell us about energy in terms of reactions? And then we're going to consider why the energy gets transferred, what's actually happening that causes a transference of energy. So that's going to help you there with the first question. And then we'll just remind ourselves of the law of conservation of energy. So what do these examples tell us about energy? Whenever reactions take place, energy is either transferred to or from the surroundings. So with the combustion, we saw that energy was transferred to the surroundings, and then with the photosynthesis, we saw that energy was transferred from the surroundings. But why does this happen? Why is energy being transferred? So chemical bonds inside our reactants have to be broken down in order to form the products. Okay, so chemical bonds in the reactants are broken, and then new bonds form in the products. But why does this lead to an exchange of energy? Well, breaking bonds actually takes energy in. Energy is required to actually break those bonds. But when the new bonds are made, they release energy. Okay, so we've got one system that's taking energy in, and we've got another system that's releasing energy. And so if there was an imbalance in that, then overall there's going to be a net either taking of energy or a net release of energy, which is what we see in those reactions with combustion and photosynthesis. but we'll look at that in a bit more detail shortly. The law of conservation of energy. This states that energy cannot be created or destroyed. So what that means is that the total energy that we've got in the universe is going to remain the same before and after these reactions. Okay, and that's an important concept to hold on to when we look at these processes in a bit more detail. Right, so when we're talking about reactions, we need that there's some of the language used can sometimes be a bit confusing. So if we talk about the system is the reaction itself. Okay, it's the reactants effectively. So the system is reactants and the products. So on either side of your reaction, you've got reactants on the left and products on the right. They are the system. The surroundings is everything else essentially. So in the example we've got here, it could be a conical flask, the solvent that the reaction's happening in, a thermometer, the air, a beaker. It could be anything. Okay, it's essentially anything that's not the reactants or products themselves. We've got solvent there because lots of reactions occur between aqueous solutions. All right, so aqueous means they're dissolved in water. So the reactants themselves are dissolved in water, so that the solvent, okay, the water is the surrounding. So if the temperature of that changed, then that would be an indication of either energy leaving the system or going into the system. And then the universe is basically, if we put all of these together, then that is the universe. So if the universe is always going to be the same, so you can see from this example here that if the number, so if, for example, we had system was 100, surroundings was 200, that would mean the universe was 300. And the universe needs to stay at 300. Okay, it cannot change. We cannot change the amount of energy within the universe. Okay, it stays the same. So therefore, you can see that if we decrease the amount of energy in our surroundings from 300 to 200, the only way that could happen is if the system, our reactants or products, have taken some energy in. So they would go up to 200. So we'd then have 200 plus 100 to give you 300. Right? So there's this fine balancing act that goes on. And either in our reactions, we're either going to get energy being transferred from the system to the surroundings, or it's going to go from the surroundings to the system. But either way, the total amount of energy is always remaining the same. Right, at school now, we'd have a demonstration of a couple of reactions, and you'd be able to see some temperature changes. If you're watching online, then what I suggest you do is you just look up these reactions quickly, and you'll be able to see a short video of a demonstration there. So what would happen, okay, if you haven't been to look, the copper sulfate and water, you can see very faintly on the picture there. There's a little bit of water vapor coming off, a bit of steam. That's because when we add copper sulfate and water together, that's an exothermic reaction. It gives off heat. All right. So what you'd notice is the temperature. If you had a thermometer in there, the temperature on that thermometer would go up. So the system is releasing energy. Okay, is giving off energy to the surroundings. So the temperature of the surroundings increases. On the other side here, barium hydroxide and ammonium chloride. If you get to see this at any point, this is really, really impressive. Okay, what they've done is they've between the block of wood and the conical flask there, they've just put a little pool of water. Okay, just a really shallow pool of water, and this reaction is endothermic, so it takes in energy from the surroundings. All right, so the air, the water, the conical flask itself, all of that, the temperature is going to drop dramatically, and it drops so much that it actually freezes the water between the two there, and it sticks to the bottom. Okay, so if you do get to see this, this is a really interesting reaction to see. Alright, so energy is either transferred to or from the surroundings. Okay, I've mentioned these things a little bit already, the names of these reactions. Okay, there's specific names beginning with E. Okay, so just think for a moment what these two are. Good. Hopefully you've come up with exothermic and endothermic. Now then, what we're going to do is we're going to have a few bullet points about each one of these and a couple of examples of each one of these, which you should note down. So, exothermic reactions, they transfer energy from the system, so from the reactants and products, to the surroundings. The products have less energy than the reactants. Okay, that's because the reactants have transferred that energy to the surroundings. So the products have less energy than the reactants had. This means the temperature of the surroundings will go up. And some examples of this are combustion, we saw that where we were burning fuel, neutralization between an acid and an alkali, and respiration. Endothermic reactions, okay, the energy is transferred from the surroundings, so from the solution or the air around the reaction into the system, so into the reactants and products. So that means that the products actually have more energy than the reactants had because they've drawn in that energy from the surroundings. So the temperature of the surroundings will decrease. Okay, it's losing energy, so the temperature of the surroundings will decrease. An example of this is thermal decomposition, photosynthesis, which we saw before, and instant ice packs. So those ice packs in games, PE and sports that you do, where you crack the little bag, and what that does is it starts off an endothermic reaction inside the bag, so that draws in energy from the surroundings, which is why it feels cold. Alright, here we've got Mario with our exothermic reaction graphic. This is just purely an infographic just to show you what's happening. So we've got the conical flask, and inside there we've got a reaction, and you can see from the arrows that energy is being given off to the surroundings. So the temperature of the surroundings will increase. The system, so the reactants, products, they lose energy. And then we've got delta H is negative. Right, delta H, something we've not seen yet. So delta H is essentially the energy change. So the energy change in an exothermic reaction is negative. And we'll see this more when we look at some energy profile diagrams later on in the course. But if you think about the two phrases above that, so the temperature of the surroundings increases, the system loses energy. So delta H is negative. So the system losing energy links in with delta H being negative. So if the system loses energy, then the energy change is negative. Right, we've got Elsa now with our endothermic reaction graphic. So very similar. So this time all the energy is coming into the conical flask, so from the surroundings into our reactants. So the temperature of the surroundings will decrease, and the system, the reactants and the products will gain energy, and delta H is positive. So the energy change in our system is positive. So our reactants and products are gaining energy, so delta H is positive. So with this lesson, there would be a required practical. So these are the practicals that the exam board suggests that you do. And the example we've got here is a reaction between hydrochloric acid and sodium hydroxide. And this is a neutralization reaction. So if you remember from what we've just talked about, neutralization would be an exothermic reaction. So the temperature of the surroundings would increase. And in this reaction, what you do is you start off with 30 centimeters cubed of your acid, and you add 5 centimeters cubed of your sodium hydroxide in a polystyrene cup to keep it insulated, with a lid as well to keep it insulated to stop that heat escaping to the surroundings. And when you've added your 5 centimeters cubed, you watch the temperature rise on a thermometer, keeping a really good eye on it, and when that temperature stops going up, you note down what the temperature was, and you add another 5 centimeters cubed, and you do the same thing. You watch the temperature and note down the temperature when it stops going up, and then you add another 5 centimeters cubed, and you keep going and going until you've added 40 centimeters cubed of sodium hydroxide in total. And then you'd wash out all your equipment and you'd do it again. Right, the instructions are there. They're very small, so if you want to pause the video and read through those, you can. And it also says to try and produce an equipment list from the method. Right, so we're kind of doing things in reverse there. So if you pause and have a go at that now. Right, so here we are. Our equipment list. We needed hydrochloric acid, sodium hydroxide, polystyrene cup and lid, beaker, measuring cylinder, measuring cylinders, and a thermometer. All right, you would also be expected to be able to draw your own results table in order to record the data. Right, that brings us to an end of today's lesson. The required practical, you can find videos for that online as well, or if you're at school with me, we would be doing this in the classroom. But next time we'll be looking more into those energy profile diagrams, and I hope to see you then.